In this video, we examine the spherical harmonics, which are the wave functions for the stationary states of the rigid rotor. For such a rotor, such as a diatomic molecule, the Schrodinger equation is h hat operating on y, jm, of theta and phi equals to ej times y, jm, of theta and phi, where each rotational state is characterized by two quantum numbers, j, which can be 0, 1, 2, or so on, and m, which can assume values between minus j and positive j. J is often labeled as L, lowercase l. The energy eigenvalues for these states are Ej equals to h bar squared over 2I times j plus 1, where I is the moment of inertia. These energies only depend on j, but not on m. So for each j, all states with different m have the same energy. The wave functions y, jm are called spherical harmonics. They are defined over the surface of the sphere, and you can look at them as waves on the sphere. Their general form is the following: y of jm of theta and phi equals sm times nj magnitude of m times pj magnitude of m of cosine theta times e to the positive I m phi. The expression consists of four factors. The first factor is an overall phase, and it is a matter of convention. The most common convention is to have it -1 for positive odd m and +1 otherwise. The second factor is the normalization constant. That assures that the wave functions are normalized in the sense that the integral over the sphere surface of y star y equals 1. So the integral from 0 to 2 pi, the integral from 0 to pi of y jm complex conjugate times y jm times sine theta d phi equals 1. Note that the integral runs over the entire sphere. Phi runs from 0 to 2 pi, and theta runs from 0 to pi. Also, make sure you always include the sine theta factor in this type of integrals. The third factor is an expression that only depends on theta. These functions p are known in mathematics, and they're called associated Legendre polynomials or functions. So pjm is an associated Legendre function. For a given j and m, you can look them up in a table. They get more complicated with increasing j. The last factor, number 4, contains the phi dependence. It is fairly simple, just a complex exponential, which depends not only on phi, but also on a quantum number m. It will be possible to write down a full expression for the normalization constant, second factor, and a more explicit form for the associated Legendre functions. However, whenever you need a spherical harmonic function, it's easiest and best to look it up in a table. To get a feel for the general anatomy of these spherical harmonics, let's look at a few spherical harmonics with small j. The spherical harmonic representing the ground state has j equals 0, and it's given by y 0, 0 equals to plus square root of 1 over 4 pi. This is a constant, independent of theta and phi. It means that if you go measure the orientation of the rotor in the ground state, you're equally likely to find any orientation. For j equals 1, the 1, 0 spherical harmonic is positive square root of 3 over 4 pi times cosine theta. Now there is a theta dependence. Recall that theta is the angle down from the North Pole. Now this contains cosine theta, so the function is 0 when theta is pi over 2. That's at the equator of the sphere. So there is one node, and the function has two halfways, from North Pole to the South Pole. The other spherical harmonics for j equals 1r, y1 and plus minus 1, equals to negative positive square root of 3 over 8 pi times sine theta times e to the positive negative I phi. Now we see the phi dependence as well. That makes the function complex. Also, due to the sine theta factor, this function is never 0, except at the North and the South Pole. Lastly, you also can see that our phase convention kicks in and puts a negative sign in front of the whole expression for m equals plus 1. For j equals 2, the simplest harmonic j20 is equal to positive square root of 5 over 16 pi times 3 cosine squared theta minus 1. Since m equals 0, there is no phi-dependent complex exponential. However, the theta dependence got a bit more complicated. Next comes y2 plus minus 1, so m equals plus or minus 1. It's given by minus plus square root of 15 over 8 pi times sine theta cosine theta times e to the plus minus I phi. And the last harmonics for j equals 2 are y2 plus minus 2. And they're equal to positive square root over 15 over 32 pi times sine squared theta times e to the plus minus e2 phi. You see that the theta functions for all j equals 2 functions contain a product of two trigonometric terms, cosine squared, sine times cosine, and sine squared. As j increases further, these theta functions become more and more involved. Last, let's look at orthogonality. Spherical harmonics form an orthonormal set over the sphere. This means every function is normalized by itself, and each pair of functions is orthogonal. Mathematically, we can write both these properties in one go. So the integral from 0 to 2 pi and the integral from 0 to pi of y j prime m prime complex conjugate times y j m times sine theta d theta d phi equals to delta j prime j times delta m prime m. Here, the two deltas are Kronecker deltas. The first one is equal to 1 only if j prime equals j, and 0 otherwise. The second one works analogously. Overall, only if j prime equals j and at the same time m prime equals m is the entire integral equal to 1. Otherwise, it's 0. In summary, we have looked at the general structure of spherical harmonics and at some specific examples. Spherical harmonics form an orthonormal set.